All right, pre-calculus honors back with another instructional video. This is optimization day 5. Okay, start with a little bit of a homework review here. Hopefully you took a look. This first homework problem right here, number 2 from that ditto. I think it's 2.3, more optimization problems, something like that. Nice little rectangle. Okay, it's based on the x-axis, upper two vertices on the parabola y equals negative x squared plus 9. We want to know the largest area the rectangle can have. Okay, so look, we drew it out here. This is a calculus solution. Okay, you should be able to graph this thing without a calculator anyway. It's just negative x squared shifted up by 9 units. If you really need to use the calculator to graph it, not the biggest deal in the world. But remember, infinitely many rectangles that could be here, okay, depending on where this point is right here. You know, maybe the point is up here, and that means you'd have a counterpoint over here, and the rectangle would be tall and thin. Okay, but maybe you'd actually have this point down here, then you'd have a counterpoint over here, and the rectangle would be short and fat, like Mr. Berto, okay? You know, and there's really infinitely many. The one of largest area is going to be as close as possible to a square. It's usually the way these things work. Anyway, maximize area, okay? And that means I got to get an equation for that thing. And remember, the difference with these problems right here is that there are already variables defined, okay? So even if you want to say the base of the rectangle is b and the height is h, at some point you got to say b is equal to 2x and h is equal to y, because the only relationship they give you between two variables here is that, you know, this point must lie on the parabola y equals negative x squared plus 9, so you got to have that relationship between x and y, that y is equal to the negation of x squared plus 9. So look, you know, this distance right here is going to be x, this distance is going to be y if you want to plot this point right here. So we know that the base is actually 2x and the height is y, and that's why the area is 2xy, as in 2xe. We got to get it down to one variable, and it's actually really easy here because they give us the relationship. So remember what I need to see? I need to see a formula for what we got to maximize and minimize in one variable. You could use this version or this version. It's just a little bit easier to use this one because we're using calculus, so we're going to have to take a derivative. Remember the domain, okay? You could always say the lower element is 0 if you want. That's the x value that makes x equal to 0. The x value that makes y equal to 0 is 3, okay? You could just set negative x squared plus 9 equal to 0 and solve, or you could realize that 3 is this x-intercept right here. So this distance, x, can only bounce back in between 0 and 3, okay? So that's something to think about. So make sure I see that domain. And if it's a calculus solution, you'll have a take-home. I'm going to give, I think it's going to be Friday night's homework, but I'm also going to give you Monday to work on it. I think that's the way I'm going to work things out. Not 100% sure right now. This is Thursday's video. I'm making it on Wednesday. Anyway, make sure if it's a calculus solution, I see the derivative, and I see that you set it equal to 0. Don't just go right to x equals radical 3. Unless you have it set equal to 0, you can't solve any equation. I don't need to see these two steps. You want to go right to x equals radical 3, that's fine. Don't worry about units here because they don't give us units, but that's something to think about in other problems. Make sure you draw that line. You got to show me that there's actually a maximum when x is equal to radical 3. And how do you do that? Draw that little A prime line right here. This line next year on the AP, it won't mean anything, okay? It won't mean any type of justification. It'll be a great way for you to actually organize your work, okay? Something we'll speak about, we need to next year. But the fact is, nobody knows what this means besides you and I. So you got to write down a little blurb. Say this means you have the maximum area, the maximum of the area function, because its slope changes from positive to negative, at x equals radical 3. Then after that, you got to solve the problem. What the heck did they want? Oh, they actually wanted to know the largest area. Okay, so that means you could either plug that radical 3 into this area formula, which is extremely annoying without a calculator. It's a lot easier to actually get what y is equal to by plugging into negative x squared plus 9. And then you could actually use area equals 2xy to get what that maximum area actually is. So just make sure you solve the problem as well. So hopefully not really too terrible. It's a pretty popular type of problem right there. You know, we had these cube problems right here. Two positive numbers whose sum is 20. Product as large as possible. Maximize product. I called the numbers a and b. So the product is a times b. And here's our relationship, right? A plus b is equal to 20. Too many people, they see two positive numbers whose sum is equal to 20. They write this down right away. They get confused. Remember the steps, okay? Find out what to maximize and minimize. Product as large as possible. Get an equation for that thing. Get it down to one variable. Get a domain, okay? And a is a positive number, so it can't be 0 and it can't be negative. It's got to be greater than 0, and that means it has to be less than 20. If it was greater than 20, if a was, say, like, 21, then b would have to be -1 to get an answer of 20 right there, and b can't be negative. So once again, this is just the value of a that makes a equal to 0, and this is the value of a that makes b equal to 0. Hopefully getting a domain not too horrible for you at this point in time. It's really only useful for those calculator solutions, but it could be really useful then because it could be annoying to actually get a picture with those types of situations. We'll do one of those in a hot minute. Anyway, take that derivative, set it equal to 0, solve. No units here once again. Draw that line. We can see you have the maximum product when one of the numbers is equal to 10, which means the other number has to equal 20. So this is actually supposed to be a pretty easy problem, just like number 6. Here we have two positive numbers. They tell us the product is 81. They want the sum to be as small as possible. So minimize a plus b. I called that sum. And we know a times b has got to equal 81 because the product is going to be 81. So I use that to get it down to one variable. Okay, get that domain. And here you could actually try setting b equal to 0. But it's never going to happen, Captain, okay? If you cross multiply here, you end up with 0 equal to 81, which hopefully is not true, okay? Because that's a strange equation. And the idea is that you can't have a being equal to 0 because this would be undefined. And you can't have b equal to 0 because you get an unsolvable equation. What's going on conceptually is you're saying that when you do a times b, you get 81. So essentially you're saying in your math here that there's no way for either of them to be 0 because then the product would be 0. So once again, if you just put that normal domain, you're going to be fine. Take your derivative, set it equal to 0, solve. Okay, draw that s prime line in this case and make sure you actually explain the line, minimum sum when a equals 9, and then they actually want the two numbers, so you want to get b equal to 9 as well. So hopefully not too terrible, those two problems there. Let's do this. Let's hop to same packet. So I think it's 2.3. It's a ditto optimization problems. Let's take a look at number 5. Okay, in number 5, we're going to do a calculus solution and a calculator solution. So calculus and calculator solution. Calculator. So this is crazy. We're going to do this problem twice right here. I don't know. You guys ready? Come on, let's go. All right, we have a 216 square meter rectangular pea patch is to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. A lot of words. What dimensions for the outer rectangle will require the smallest total length of fence, and then how much fence will actually be needed? Okay, so look, we want to know the dimensions for the outer rectangle that require the smallest total length of fence, and then we're going to want to know how much fence is needed. So smallest total length of fence, we know we want to minimize total length of fence. You know, and usually people don't really struggle so much with the calculator or the calculus here. It's the algebra, the geometry that bothers people. 216 square meter rectangular pea patch. All right, so here's your rectangular pea patch is to be enclosed by a fence. There's my fence right there, has 4 sides. But then it says it's going to be divided into 2 equal parts by another fence parallel to one of the sides. And there are so many different diagrams you could have here, okay? You could have your fence right here in the middle, or you could have your fence looking like this. I'll draw mine that way. You could have different diagrams, and you could even label things differently, but then end up with the same answer. So there's a lot of ways to do these problems. The idea is that we don't know the dimensions here, so maybe I'll call this dimension x right here. I'll call this whole dimension y, which you don't need to do. You can call each of these pieces y if you want to. It still works out. The work just looks a little bit different, but you still end up with the same answer. I'll do it this way. I'll put x here, so that means this distance is x, and this distance is x, and this whole distance right here is y. And if you want to minimize the total length of fence, okay, so minimizing fencing here, maybe I'll say f equals fencing. The thing you want to maximize and minimize, it's always going to be unknown, okay? I'm not going to know what the actual amount of fence is. I want to minimize that, okay? So I don't know what that is. That's variable, but I know it's x plus x plus x plus y, and that's 3x plus 2y. You know, like I said, maybe this distance is y right here. So you'd actually have 4 y's. You can make it 3x plus 4y. It'll still work, okay? We have our criteria here. The area has to be 216 square meters. So x times y equals 216. Once again, if you had these both labeled as y, you'd have x times 2y is equal to 216, and things would end up working out. Solve for either. I'll solve for y just because it seems right to do. Okay, and here we have f is equal to now 3x plus 2 times 216 over x. And I'll simplify it a little bit. You can even call it f of x if you want to, or just leave it as f. It doesn't make a difference. But f of x is just something we know and love so much, so why not have it there? 3x plus, I don't know, 2 times 216. What is that, 432? What is it, that time already? Oh, can't tell offhand. Anyway, so here we have 432 over x, or 432 times x to the negative 1. Come on, that can't tell offhand joke was good. And look, we need a domain. And some people are like, I don't understand the domain. I don't know what's going on. But they realize it has to be in terms of x. And you know x always has to be greater than 0 if it's a geometric situation. So if you put that, it's actually the correct domain, okay? You can't include the 0. Rarely do we include the 0. Sometimes you can include it. But it's silly to put there, okay, because it just implies you could have like a minimum anyway, that if you're not looking for a minimum, that, you know, like maybe minimum area, something like that. So look, you don't need to really include the 0 ever. Sometimes you can include it, but it's also if you just ignore the inclusion anyway, because it really doesn't make a difference. But here, if you try to set y equal to 0, once again, a fraction can only equal 0 when its numerator is equal to 0. And this numerator will never equal 0. You set this equal to 0, you get 0 equals 216. There's no value of x that's going to make that true. You're forcing this thing to have an area of 216, which means both of these dimensions must exist. Okay, the x has to be a number greater than 0 and the y has to be a number greater than 0, hence why this is the domain. Regardless, calculus solution, let's take that derivative, let's derive. I will derive. Okay, and here I get 3 minus 432 x to the negative 2. Don't forget to set that puppy equal to 0. Ruff, ruff. Okay, and we get 0 equal to 3 minus, all right, is 432 over x squared. You got to show me you're setting an equal to 0 at some point. Add 432 over x squared to both sides. All right, little cross multiplication action, which Mr. Harrington can't stand, but it's a valid mathematical technique, so I don't know why he's got to have such a problem with it. Anyway, divide by 3 on both sides. I don't know, man. 3 into 432, I got to write it down over here. 3 goes into 4 one time with 1 left over. 3 times 4 is 12, so 1 left over. So 144, which is great, right? Because now we know the square root of 144 is actually positive and negative 12, but we only worry about the positive because x represents this distance. Units! I need units indeed, okay? They said area was in square meters, so x, which is just a linear measurement, will be in 12 meters. And some people are like, oh, we're done with the problem. No, now you got to show me that there's actually a minimum at this x value. That's where I draw the line. The f prime line, the old f prime line coming back. 'Tis it bounded. It's bounded on one side, okay? The f prime line is going to be starting at x equals 0 and ending when my wife stops nagging me. Never! All right, so here we're going to put all those critical x values on the f prime line. Any place where f prime is equal to 0, that'd be your 12 right here. You know, maybe plug a 1 back into f prime. Here's probably the best f prime to plug into. 3 minus 432 divided by 1 squared is really 3 minus 432, which is going to be negative. Remember, this is a place where that fencing function would have a derivative equal to 0, so it has a horizontal tangent. I don't know, maybe plug in a 20. Right, if you plug in a 20 here, 20 squared is 400. 432 divided by 400, okay? It's obviously going to be a number bigger than 1, but it's going to be less than 3. Okay, 3 minus a number less than 3 is going to be positive. And here you can see if f prime changes from negative to positive, f, this fencing function that we're thinking about, has to change from decreasing to increasing, which means it's going to have a minimum. So now we know min length of fence, fencing, on guard. We'll say when x is equal to 12 meters. And then look, that's the blurb that describes the line. And now you gotta be like, wait, what the heck did they want? They wanted two things, right? They actually wanted the dimensions for the outer rectangle that require the smallest total length of fence. And then they actually want to know how much fence must be needed. So one dimension is x. The other dimension is y. Y is 216 divided by x. So 216 divided by 12. That's going to be 18. Okay, so y is equal to 18 meters. That answers the first part, right? That's our dimensions. Now they actually want to know how much fence will be needed. So the min amount of fence, so min fencing, on guard. Any formula you want here, okay? You could use the formula in terms of x only. You could use it in terms of x and y. Let's do that. I like using that one. So 3 times x, 3 times 12, plus 2 times 18. So what does that give us? 36 plus 36 again, so 72. And I need my units, and that's going to be meters, okay? Because fencing is actually going to be a linear measurement. It's not really so complicated to do the solution. It's just the algebra that bothers people. On your take-home, you're going to have a take-home. It's going to deal with two big problems from this topic. One, a calculus solution. One, a calculator solution. They'll be like other problems that we did, okay? So there really shouldn't be many surprises here. You know, I'd like to test you a little bit more vigorously, but people got a lot of stuff going on right now, so I don't want to put an extra, piece of anxiety into your lives. Just be vigilant. Make sure you do this work, especially if you want to take AP Calculus next year and BC Calculus. I mean, don't even get me started. Like, you better be on the ball and know what you're doing. But once again, no pressure with grades and things like that. Let's not go crazy with stuff like that. This take-home will also have some problems from curve sketching. Remember, you had that quiz. We never had, like, a bigger assessment. So I think there's, like, 6 multiple-choice curve sketching problems and then 2 big optimization problems. Technically, the 2 topics go hand in hand anyway. Hey, we were supposed to do this by calculus and calculator, so let's do this by calculator now. So this was the calculus solution. So calculus. I just read several memes that Isaac Newton, the inventor of calculus, did so during the plague, okay? So if during, the coronavirus outbreak right here, you're at your home and you're inventing new mathematics, good for you, okay? We'll talk about it when I see you. Now we'll do a calculator solution. So we'll go calculator. What did one calculator say to the other calculator when they were leaving each other? Calculator, instead of like, see ya later. Anyway, calculator solution. Okay, remember, we still start with the function for what we need to maximize and minimize in one variable. So f of x equal to, what was it, 3x? Sometimes I say that's thrix, and thrix is for kids, so that's for you. Plus 432 times x to the negative 1, or the same thing as 432 over x. We're not taking a derivative here, so why not write it in that pretty way where x is greater than 0. Remember, we don't take a derivative now to figure out where this has a minimum. We actually graph it, put it in the calculator, and don't forget to label those axes. We know the independent variable is x, so x has got to be the horizontal axis, but the vertical axis here is not y, it's f. People are like, I'm going to label it y anyway. You can't, okay? You already said y is this distance right here. Why would the vertical axis label this distance right here? That would be a function that represents a relationship between x and y. It's not what we have here, okay? We have a function that represents a relationship between x and f of x. Let's go to the calculator. Calculus. Okay, let's actually graph this puppy. Okay, and here we have 3x. Plus little alpha y equals for sheequies, okay, 432. Number of dates I have this weekend divided by x, okay. And remember, the problem is when you want to graph this, people are like, yeah, just zoom 4. That's what Berto says to do. Zoom 4. Let's see what kind of picture we got. Thanks a lot, Berto. And people are like, I'll go with zoom 6. That was my old standby. I always like to zoom 6. Berto told me it's no good, but I'm going to zoom 6 anyway. Maybe I should hit the button. Okay, zoom 6, here we go. He's never let me down. Zoom sticks rhymes with candlesticks, and that's what Jack jumped over. And what's going on? A little spinning circuit. Nothing's going on, okay? These numbers are much bigger. You're not going to be able to use those normal windows that we use, okay? So look, speaking of windows, she came in through the bathroom window. All right, hit the window button. And look, we know the x-min is 0. We don't know the x-max, okay? We want to take an intelligent guess. Play around a little bit. X times y is equal to 216. I'm looking at down here. So x is probably going to be something smaller than 216, but you also want to make sure you pick something bigger than x is because you want the x to kind of be in the middle. The 216 might be a little extra. Let's see. Let's try and make the x max equal to 216. Then zoom Mr. Pushy's IQ, right? Zoom 0. All right, and believe it or not, you could see the minimum right there. You know, you can see we went out way too far as what x is equal to. Okay, so if you want to, you can make x smaller if you want. I don't know, don't make it like, 210. You know, go big or go home. Maybe half of that. What was half of that? What is it? 100 plus 8, so 108. You know, sometimes you might actually end up making it too small. Let's zoom 0 again. See what this looks like. That's pretty sweet right there, not for nothing. We even went out way too far, but this is good enough. And don't sketch it this way, okay? Some people actually sketch it this way. I'll show you over here. All right, and they'll show me the sketch, and they'll draw it like that. And then they'll actually calculate the minimum point, and the minimum point won't have a y value of 0, or in this case, an f value of 0. So your sketch will be wrong, okay? Right now, it looks like this minimum is on the x-axis. That's not true. When you go back in through the bathroom window, you'll see when you zoom fit, weird things like this happen. The y minimum is 72. I want it to be 0 if I could actually see the x-axis. Then hit graph, don't rezoom. Okay, and that's what you want to be sketching. And remember, it doesn't really matter what's happening on the outsides of the graph. It just matters this point right here, okay? And that's that minimum point that we got to calculate. Let's calculate that minimum. Come on, bug, bug, a bug, a bug, 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 a bug, 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 bug. All right, and then bug again to the right. Okay, and I get the minimum at, let's take things with a grain of salt here. We'll say that's 12, 72. Okay, and then we answer the question, right? They want to know the dimensions for the outer rectangle for it to require the smallest total length of fence. Well, remember, this 12 right here represents X, right? Okay, and this 72 right here represents F. So I know that we have that min fencing when, I don't know what word I just wrote that's supposed to be fencing. Who could spell? Not me. When X is equal to 12 meters. Okay, you can't read what I'm writing over here. So minimum fencing when X is equal to 12 meters. And then that means Y is equal to 18 meters. Just plug back in. And then you can actually go right to this value, 72. That represents F. That's the min amount of fencing. Okay, so min fencing. And that's going to occur with 72 meters of fence. Okay, just like we got before. What's that feeling? You can only say what it is in French. A deja vu, okay? And that's what we have right here. So look, you'll have a calculator and a calculus solution problem to do on your take-home. You know, probably give that out Friday. It'll be Friday's homework for over the weekend, but I'll probably give Monday for you guys to work on it anyway. So I'm not really 100% sure what I'm going to do, but we'll figure things out. Anyway, so that's, optimization. I believe this was day 5 right here. And optimization, day 6 coming at you tomorrow. Until then, friends, we're on a little bit of a break, and I'll see you then. Adios.